This is going to be a fairly short video because this concept of differentiable is something that we're going to do a math lab on next class. So in the video I'll present the definition of differentiable and how that's going to be two one-sided limits if necessary. And I'll take you through the connection between differentiable and continuous, continuous being an adjective you already know. And then you'll come to class hopefully ready to use these definitions to work on your lab. Alright, so a function f is said to be differentiable at x equals a if this limit exists. And you'll recognize this limit here from last class as being the calculation for finding the slope of a curve. So what we're saying is a function f is differentiable at a if there is a slope at a. Now, this is a pretty straightforward definition. You take your function f, you subtract f of a, divide by x minus a, and you try to calculate this limit. Where it may get a little hairy is when you have a piecewise function that splits at x equals a. And if that is the case, then this limit has to be broken into two one-sided limits because we know that a limit exists only if the two one-sided limits exist. So one thing you'll have to do in your lab is, on a few of the problems, is to calculate this limit. You're going to have to do two one-sided limits and see if they agree or not. Okay, so I'm going to say another way of presenting that statement, limit as f of x minus f of a over x minus a, limit as x goes to a exists, means that these two limits here must be equal. So there's your left-hand limit, and that must be equal to the right-hand limit for that full limit to exist. So that should look very familiar. This being a concept for a limit existing, we use it in the definition of continuity as well. Okay, so those two things being equal imply that this limit exists. Now, one important theorem that is useful is that if a function is differentiable, then it is also continuous. So differentiability implies continuity. And I'm going to take you through a proof of this fact on this yellow slide here. Again, this is testing your heart for mathematics. This is something the mathematical mind's really interested in, and getting down the nuts and bolts of why something is true. Okay, so what we're saying here, a function being differentiable, which says this limit existing. Okay, so somehow this limit existing somehow implies that f is also continuous, and the definition of continuity, if you'll recall, is limit as x goes to a of f of x is equal to f of a. Okay, so somehow we're going to show that this being true implies that this is also true. We start off with something that we know is true, and again, you may not know why you would start in this place. And again, it comes with experience and working with proofs and how they're structured. But we start with something we know is true, and this f of x minus a is going to show up in several locations, so it's a natural place to start. And we say that by the reflexive property, f of x minus a is equal to f of x minus a. Now, I'm going to multiply both sides, or sorry, not both sides, but top and bottom of the right side by x minus a over x minus a. This is essentially multiplying by 1, but I have to say somewhere here that x is not allowed to be a. And what I'm going to do now is just rearrange the right side a little bit. So I would like to have f of x minus f of a be over x minus a. You may see where this is going, but this is part of the definition of differentiable. So I'm borrowing this denominator, and I'm going to put the x minus a over here over 1. F of x minus f of a is still on the left side. Now, I'm going to take the limit as x goes to a of both sides. Remember, this is not plugging x equals a in. This is just saying what happens close to values of a. So there's the left side. Now the right side, I'm going to break this into two pieces. Okay, the limit as x goes to a of this first piece, f of x minus f of a over x minus a, times the limit of the second piece. So times the limit as x goes to a of x minus a. Now, the first piece is the definition for f prime of a, if it exists. But by hypothesis, this limit does exist. Okay, so I should have put in the beginning here that limit existing. Okay, implies that this is true. So this limit exists, and we have a symbol for it. We call it f prime of a. Now, what's the limit of this second piece? Okay, well, I do a plug-in, and I'll get a minus a, or 0. So I have f prime of a, which is a number, times 0. Overall, the right side comes out to be 0. Now, the right side, let's also split this into two pieces. The limit as x goes to a of f of x minus the limit as x goes to a of f of a. Now, f of a is a number, and the limit of a constant is the constant, so that just becomes f of a. So I still have the limit as x goes to a of f of x, subtracting f of a equals 0, and if we move f of a to the other side, you'll notice something hopefully that's familiar. This is the definition. Oops, looks like I forgot the f of x there. This is the definition of a function f being continuous at x equals a. So what we've done is we started with a hypothesis that f prime of a existed, and we worked down using logical correct steps until we got to the definition of continuity. So if you're told a function is differentiable, it's automatically continuous at that same spot.